I think we can get it started. So hello everyone, welcome to Ask Seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Melanie. Kathy is our communication specialist, and Kathy and I will be today's moderator. And we are excited to have our speaker, Professor Tiffany Shaw, joining us from University of Chicago. Just so you know that this seminar is being recorded and will be later published on our YouTube channel. Please be free to ask questions. You can do so by raising your virtual hand, and we will unmute you. You can also send us a message in the chat. Please allow me to introduce the speaker briefly. So Professor Tiffany Shaw is an associate professor of geophysical science at the University of Chicago. Her research focuses on the physics of the atmosphere and climate system. She's a fellow of the AGU and a recipient of an NSF Career Award, Sloan Fellowship, and Packer Fellowship for Science and Engineering. Okay, so I will give the ball to Professor Shaw, and Professor Shaw, please proceed.
Okay, thank you, John, for the kind introduction and for the invitation to be here today. Hopefully you can all see my screen.
Yep, looks
okay. Great. Thank you for confirmation. So I am, as John said, a climate theorist, and I'm excited to be here today to talk to you about reconciling past, present, and future storm track intensity changes by incorporating the role of surface heat exchange. And so I just want to begin by acknowledging the challenging year we've all faced. Particularly, we have a young son at home. It's been quite the ride. But I just want to, again, acknowledge that I'd, of course, much rather be there with you in person today, but very, very grateful to be here with you virtually. And so as a big picture kind of climate theorist, I'm interested in understanding, the Earth in these three different Goldilocks states, as I'll be using them today. So in the middle, obviously just right, the modern climate. To the left, you see an artist's rendition of the Snowball Earth. So this is something that occurred 600 million years ago in Earth's history. We have geologic evidence for, and that would be too cold. And then on the right will be the Goldilocks too warm. We think of this as the future, the projections to business as usual emissions scenario. So today's talk is going to focus on storm tracks, and I'm going to define what that means because I'm particularly thinking about mid-latitude cyclones, so not tropical cyclones. And in mid-latitude, storm tracks are the dominant feature. So here's a beautiful image of a mid-latitude cyclone. And the reason, of course, we can see this cyclone is because it's moving warm and moist air poleward and cold and dry air equatorward. And for someone like myself who lives in Chicago, these mid-latitude cyclones are extremely important for our day-to-day weather. But they're not just important for Earth's weather, they're also important for Earth's climate. As we aggregate these cyclones together in mid-latitudes, they play a fundamental role in Earth's energy balance. And so from this planetary scale perspective that I used with my Goldilocks climates, that's really the metric that I want to be thinking about. And so in particular, this northward heat transport is a quantity that I am going to be targeting. And so let's take a look at it here, estimated from reanalysis data, ERA-Interim, the best known estimate of the Earth's atmospheric state that combines both models and observations. And so how we calculate this northward energy transport is to, on this latitude-longitude grid, is to take the north-south atmospheric motion, as you saw encapsulated in that individual cyclone, and we multiply it by the dominant forms of energy. Internal energy proportional to temperature, latent energy proportional to humidity, and potential energy. We vertically integrate it. We would also have bandpass filtered it to extract the time scales relevant for mid-latitude cyclones on the order of a week. And then we weight it by circumference. And having done those steps, we end up with a unit of energy, watts, joule per second, and the P indicates petawatts, which is 10 to the 15 watts, so a huge amount of energy. what you can see in the map is that the northward energy transport, the energy transport is northward toward the Arctic, so that's positive in the northern hemisphere, and negative, which is southward towards the Antarctic. You can also see the localization of the North Pacific and North Atlantic storm tracks that we can also quantify with other metrics. So for today's sort of planetary scale perspective with these Goldilocks climates, I really want to focus in on a broad metric. So a metric that encapsulates this red box, a longitudinal average from 0 to 360, and then an average in latitude, area weighted average from 20 degrees to 60 degrees. And we do that because, you know, we're interested in these sort of big changes that are going to occur as we look across these climates, and we want to fundamentally understand, you know, what are the big levers, what are the things that are responsible for changes in the mid-latitudes. So the focus of the talk, the centerpiece of the talk today will be answering this question, which is what controls storm track intensity, namely how much, in this case, poleward energy transport that we get across these three Goldilocks climates. So too cold, the Snowball Earth, just right, the modern day, and too warm, which is the projections to business as usual emissions scenario. Of course, you know, I stand upon the shoulder of giants. You know, the theory of baroclinic instability tells us why storm tracks or mid-latitude cyclones exist. And in conjunction with that, we have estimates of their growth rate, the ED growth rate, and also estimates of their energy cycle from the mean available potential energy. And all of those theories that we've developed, which exclude the role of condensation or latent heat release, point directly to the importance of the equator-to-pole temperature gradient. So when that near surface equator-to-pole temperature gradient increases, we would expect the storm tracks to strengthen. And when that equator-to-pole temperature gradient decreases, we would expect them to weaken. And so, you know, it begs the question, you know, does that work across all these instances? Is that, you know, the right perspective? Is that a good theory? Now, in the context of just right, we know there are some discrepancies, in particular in the North Pacific. If we look at the storm track evolution seasonally, it does not coincide with the equator-to-pole temperature gradient. But let me also now look at these other climates and establish whether temperature gradients can be a good intuitive thing to keep track of when trying to understand storm track intensity. So we start with too cold. Let's look at some previous work by Ray Pierre-Humbert, who simulated the response to Snowball Earth conditions. So we don't have direct estimates of storm track 600 million years ago, so we rely on these self-consistent simulations where we put ice everywhere, changing the boundary condition, and then simulating through general circulation models what the storm tracks would look like. And here the y-axis is a percent change as a function of month. Southern hemisphere storm track intensity is the black line, and the northern hemisphere storm track intensity here is the blue line. Clearly, there's a dramatic weakening of the storm tracks independent of season and independent of hemisphere. And when we go and compare this bulk metric of storm track intensity to one of these theories that focus on the equator-to-pole temperature gradient, namely the so-called ED growth rate, we see the dashed lines. And so obviously there's a lot more seasonality in these dashed lines, but I want to draw your attention particularly to winter in the northern hemisphere and winter in the southern hemisphere, where by this metric we would expect the storm tracks to strengthen, and they don't. So this metric, though, it does make sense why it would predict a strengthening. The temperature gradient is actually much larger in wintertime in the Snowball Earth than it is when we consider the modern conditions. And why is that? Well, ice has a very low heat capacity in polar night, which is winter. Ice cools off very efficiently, and we get very, very cold temperatures over the poles. And that's a larger gradient than even we have in modern. But ultimately, what we see here from this example is that surface temperature gradient or near surface temperature gradient does not control storm tracks when it's colder. So let's move on then to when it's warmer, which would be the simulations of the storm track in response to business as usual emissions, which would be end of century here. And this is taken as motivation by work by Paul O'Gorman. So we look at the percent change once again as a function of month with the same color coding. So southern hemisphere storm track intensity is solid black, northern hemisphere is solid blue. And you can clearly see in the south, the expectation is that the storm tracks will strengthen independent of month, whereas in the north, we have strengthening in winter and weakening in summer. But again, comparing to this metric based on temperature gradient, near the surface, which is this ED growth rate, the dashed lines, there's just not a good agreement, particularly in the southern hemisphere. And so as a theorist, we take all of this together now. More than one instance do we find a disconnect between this quantity that we're very used to thinking about and intuiting about this equator-to-pole near surface temperature gradient. Now in these many instances, feeding it into our theories, it just doesn't give us the right intuition. So something is not right. And that's really the subject of the talk today. And so, okay, well, if it's not near surface temperature gradient, maybe I'm overly focusing on that. Why not look aloft? That's a fair question. I think, though, we run into the challenge when we look aloft that the storm tracks are influencing the temperature there. So we get a kind of a chicken and egg problem. We can't disentangle how much of the temperature is shaped by the storm tracks themselves. So let's step back then and consider this question across these Goldilocks climates and not throw out temperature altogether, but bring it in with a slightly different perspective and see if we can come up with a holistic situation, a holistic set of a holistic factor or mechanism that's going to allow us to reconcile the changes, really dramatic changes across these three Goldilocks climates. So that's the motivation today. And before I get into the work that we've done, I want to acknowledge the contributions from current and former members of my group. Starting on the left here with the too cold climate, R.J. Graham, who's a former undergraduate at the University of Chicago and is now a PhD student at the University of Oxford, did his undergraduate thesis on the circulation of Snowball Earth. In the middle, just right climate, we have Pragava Barpanda. She's a former PhD student in my group and is now a postdoc at the University of Colorado with George Kalatis, and she's looked at the hemispheric asymmetry of storm tracks in the modern climate. And then moving to the right, too warm, Zoe Smith is a current undergraduate at the University of Chicago, and she is working on the storm track response to Arctic sea ice loss. And Jihong Tan, a former postdoc in my group who's now at GFDL, has been looking at the longer term response to business as usual scenarios of the storm track. And so if we're targeting this question and we're trying to move away from surface temperature gradient, I think it begs the question, well, what else can we bring to the table here? And I've chosen these three images because I think they illustrate some pretty dramatic changes that we might want to leverage, in particular in the surface conditions. So if we look over on the too cold end, obviously we're looking at now a very bright reflective planet, because what was previously a blue and white marble is now completely white. And that really is reflected in the fact that the surface albedo has increased from, let's say, mostly ocean to an ice albedo. And of course, what happens over the ocean in the just right climate is we get a lot of absorption of sunlight, and that drives evaporation. And so if we've covered the planet with this bright reflective surface, we've prevented that absorption of sunlight and also prevented any evaporation. So that should have huge and dramatic implications for this planet, particularly in the regions where evaporation is large, such as the subtropical oceans. And then if we move over to the right, to the too warm climate, in the perspective of albedo, particularly on the shorter time scales, we expect to lose Arctic sea ice. And that would have the opposite change of albedo, where we would decrease the albedo because we're taking a reflective surface, we're melting it and getting a darker ocean surface underneath. With that darker ocean surface, we have the potential to absorb more sunlight, and that absorption of sunlight can act as a source of energy to drive evaporation. But that's really on short time scales. As we look onto longer time scales, which would be late in the century, when the oceans have begun to realize the warming, and particularly in the subtropical oceans, we would expect evaporation to increase significantly there. because we know that warmer air holds more moisture. But it's not just that. The warmer you are to begin with, the more moisture you will be able to hold, because there's a nonlinearity from Clausius-Clapeyron relation, as we'll see. And so if we, envision these surface boundary condition changes now on the left-hand side rather than temperature, and we try to use them to intuit some change in intensity, given the existing frameworks, we really just can't do it. And the reasoning is that what these frameworks require above this arrow is temperature, and these quantities are not temperature. In order to extract the temperature response, we'd have to feed these into a model that predicts temperature. And so I think this kind of perspective really ultimately highlights that temperature is part of the solution of climate. It's not really part of the input. And so the challenge of having our theories rely on temperature, I think is not maybe a good starting point. And so what we're going to do today is try to build upon these left-hand side changes of the surface conditions and sort of, move away a little bit from temperature and see if we can reconcile the storm track intensity changes. So how do we do that? Well, we have to, build on something. And as a physicist, I, of course, choose a conservation law or something that has an equation for it. And in particular, I'm going to introduce for you today a framework that not only incorporates temperature, which is, of course, hugely important for Earth's energy, but also moisture and potential energy, since those are the dominant forms of energy. Kinetic is actually quite small in comparison. So how do we do this? We need to build a box model, and I'm going to introduce this to you very simply with this diagram. Of course, you can go and look in the papers for more details. So we're going to carve out an atmosphere that's bounded here by the surface, which is ocean, land, and ice, and then an oceanal top of atmosphere, which is this black line. And all we need to do is to build up all the energy transfers that we can think of, and then, create some kind of equilibrium equation or conservation equation. So let's start doing that by focusing in on the two, I would say, really important forms, dominant forms of energy transfer: radiation and conduction. So radiation is here written as a yellow contribution, and obviously it's, to leading order, the most important energy flux. We receive electromagnetic wave radiation from our sun in the form of shortwave radiation, and of course then the Earth also emits radiation proportional to its temperature. So I'm going to take those together, and in the net, those two contribute to a loss of energy. This is so-called radiative cooling. And so the arrow in yellow you see here points outward of this annular atmosphere region. And so it's a net sink. And it really doesn't have a large gradient between what I'll indicate here is the low latitudes, and then up here is the high latitudes. And as we'll see, gradients in these quantities are really what's important for the storm tracks. The second form of vertical heat transfer I've color-coded here is blue, and this is conduction. What is conduction? Well, it's different from radiation. You can think of it as a diffusive process that requires direct contact. It doesn't operate through the vacuum of space, so it makes it fundamentally different from radiation. And there's really two forms. There's the part that depends on humidity, so evaporation or latent heat flux, and the part that depends on temperature, which is the so-called sensible heat. So we take them together. And in terms of the modern climate, we know that there is a significant amount of surface heat exchange in low latitudes, dominated primarily by the evaporation of the subtropical oceans. And it's much, much smaller in the polar regions because of temperature being much colder, and also because of the coverage of the polar regions with ice. And so if we reflect then on these two regions that I've purposefully highlighted, down here, near the equator, these arrows are almost the same length. And we call this radiative convective equilibrium. But it turns out that the blue arrow is slightly larger. So there's slightly more of a source than there is a sink. And so the tropics get more energy than they lose. And then on the flip side, in this polar region, it's the opposite. There's very little input in the form of this conductive surface heat exchange, and a lot of loss due to radiative cooling. And so neither of these regions in and of themselves are in what we would say equilibrium, namely the arrows are not the same length. And so if things were to continue this way, we would be, much too cold in the polar regions and much too warm in the tropical regions. So without saying anything about causality, we'd have to deduce the existence of a third form of energy transport, which would be a horizontal arrow, so-called advection. So what is advection? Advection just implies that the atmosphere is moving and it's transferring heat and energy poleward as the consequence of the excess here in the low latitudes and the deficit in the high latitudes. But I want to separate this energy transport into two forms. One that's associated with this higher frequency storm tracks that we've identified tied to the life cycles of barochronic instability, 7 days, a week or so, versus the, the slower, more quasi-stationary circulation like the Hadley or Ferrel cells, or even Aleutian lows, these other things due to land-ocean contrast. And I do that because while this is just a budget in equilibrium, I'm going to rewrite the equation, so to speak, in words on the left there to isolate for the thing that I want to better understand the intensity of, namely storm tracks. And so if I do that, which again is just a diagnostic rearrangement, what it tells me is that the black arrow, the northward heat transport, will be a function of the imbalance of radiative cooling between the equator and the pole, the imbalance of surface heat exchange between the equator and the pole, and then the intensity of the stationary circulation. If that is stronger, then given this equator to pole gradient of the vertical fluxes, then the storm track intensity should be weaker. And so while this is just, a rearrangement and diagnostic, it's going to give us essentially a good entry point for what we wanted and what we said that the temperature-based frameworks couldn't do, which is to connect storm track intensity to albedo and to surface heat exchange or evaporation. And so that's why we pursue this. And, furthermore, we can also start to, make specific changes and get at causality through, mechanism denial type of experiments where we disable an effect. This obviously only works in models, but I think this is a good starting point for doing that. So the rest of the talk is really going to then bring to bear this framework on this, Goldilocks set of climates. And the starting point will be with the too cold climate where we've got surface albedo increasing. And as a consequence of that, we've essentially shut off surface evaporation. And then we'll move on to the other two in turn. So in each of these Goldilocks climates, I'm going to build it up, leveraging off of this box model diagram I've created, hypothesizing some kind of qualitative change, and then I'm going to make it quantitative and then test it. So that's going to be the setup for all each of these Goldilocks climates. So for the case of global cooling, we're going to hypothesize that this is really going to fundamentally weaken the intensity. And the reasoning is that it's going to decrease the surface heat exchange gradient, particularly that due to evaporation. And so let's make that clear. Where does that intuition come from? We start with this modern climate. I just walked you through that. And what we're going to do now is take, our modern just right climate and cover it with ice everywhere. And the consequence of that are, of course, manyfold, but I want to draw your attention to the blue arrows, which, of course, are dramatically smaller because no longer can we evaporate water off of the ocean. It's covered with ice. And since much of the equator-to-pole gradient of those vertical fluxes was driven by this surface heat exchange, the blue arrow, and that was, necessitating some kind of what we said advective transport, part of which was due to the storm tracks themselves. By reducing that equator-to-pole surface heat exchange, I think intuitively we would expect that the northward heat transport from advection would be much weaker. And, radiation can also change, but in the, it's mostly not changing in an equator-to-pole gradient sense. It's definitely more impacting the global mean. And so that's the sort of intuition we bring to bear, the increase of surface albedo that couples to the decrease of evaporation because the energy source of evaporation is absorption of radiation, and that would be consistent with that reduced gradient, a decrease of the intensity. So that's the qualitative picture. Now let's just give you a brief sense of how we, make this quantitative. So the surface heat exchange, which is this left-hand side term, written in a fractional change where delta is the change over different climates, can be written as a function of the change of evaporation and the change of the so-called Bowen ratio, which is just the ratio of the change of the sensible heat flux, so that diffusion of temperature, over the change of the humidity diffusion or evaporation. And if, following our hypothesis, really the change in Bowen ratio doesn't matter, then we can simplify this to really focusing in on the change of evaporation. And if we assume the change of evaporation depends most strongly or mostly on the change of saturation specific humidity, which is the specific humidity that is required for condensation, and neglecting any change in relative humidity, that's the approximation. We've actually done some work here to connect the changes of surface heat exchange to something external, something that we know, because we know how the saturation specific humidity changes with temperature. And that is through the Clausius-Clapeyron relation. So the Clausius-Clapeyron relation is the dependence of saturation specific humidity on the y-axis as a function of temperature. And so that's this blue line. It's clearly a nonlinear function of temperature. And if we consider the just right climate, and we take a pole temperature and equator temperature and we just mark them on the x-axis and we connect them with a slope, and that represents the equator-to-pole gradient of saturation specific humidity, which we've argued should be tied to the gradient of evaporation and tied to the gradient of surface heat exchange. And so that's really large for the modern climate. And it's the basis of those blue arrows that I put on that box model diagram. And so now let's envision what happens if we cool the planet globally. In this snowball case, it turns out 40 Kelvin is the nominal amount. So we subtract off 40 Kelvin from both of these values. Those are now the blue arrows, and clearly by cooling down so much, what we've done is we follow the Clausius-Clapeyron curve as it asymptotes to zero saturation specific humidity. So in this much colder climate, there really is no significant equator-to-pole gradient of saturation specific humidity, which we've are arguing is going to be connected to the gradient of surface heat exchange. And it really doesn't matter if we further change the temperature gradient, namely, we just cooled by 40 Kelvin globally. If we further say, well, actually the poles are even colder in winter, as we argued through that motivational slide from Ray Pierre-Humbert's work, it just gets worse. The pole temperature is much colder, so you move further and further to the left. You're asymptoting to zero. There's nowhere else to go. So it really is this global mean temperature that matters more than the temperature gradient. So this is how we quantify the prediction. Given 40 degrees Kelvin of cooling, we can predict a decrease of the storm track intensity. So how do we test this idea or this hypothesis? Well, as once again, Ray Pierre-Humbert says, you can't put the Earth in a jar. We can't study this in the laboratory. And unfortunately, the geologic and paleo evidence does not provide us with sufficient detail to test these ideas quantitatively. So what we rely on is a self-consistent test, given the physics that we put into general circulation models. So these are our best known state estimates of the atmosphere, based on the laws of physics. And so we simulate these climates, both a modern climate and a Snowball Earth climate with ice everywhere. And we can impose that change with just land ice and sea ice everywhere. And these were the simulations that R.J. Graham did as part of his thesis. And I just want to mention that this is a self-consistent test because this is a very nonlinear complex simulation. There are many ways where our hypothesis could go wrong, and furthermore, we can test all the assumptions that we've made following these hypotheses. So what are we looking at then? Here is to quantify the change in storm track intensity in mid-latitudes in wintertime, because that's where the temperature gradient gave us the wrong answer. And so what we find in these simulations is a 65% weakening of storm track intensity. And if we go ahead and follow the arguments I laid out from the perspective of the Clausius-Clapeyron relation and their implication for surface heat exchange, we get 85% weakening given a 40 degree Kelvin global mean cooling. And so that's clearly an overestimate. We can test this prediction, though, by quantifying the specific change that we get in the simulations for the surface heat exchange, which is weaker on the order of 60%. And so the discrepancy here is accounted for by the neglect of the Bowen ratio, which contributes about 20% of an increase because of the temperature gradient increase. Now we can look at these other terms from the box model. Radiative cooling is a contribution. It's certainly not the largest. It's about a third of the other changes, and then stationary circulation is opposite. So from the perspective of the dominant terms here, it's clear surface heat exchange is dominant as we expected, and we have some causal understanding of it through our prediction. So I just want to take a brief moment to reconcile, this disconnect we had for temperature and how did we make progress. Well, again, temperature was increasing. It had a larger gradient, and we knew that was going to give us the wrong answer with respect to the intensity change. So how does this work then? Well, the way that it's working is temperature is only one form of energy. And if we include the form of energy dependent on the latent energy, the humidity change at the surface, it turns out that that, which is somewhat following the surface heat exchange, of course, is much, much reduced. And the equator-to-pole gradient is so much has decreased so much due to the humidity gradient that it can totally compensate for the increase of the surface temperature gradient. So we get a weaker surface energy gradient, and that's consistent with the weaker storm track. So that's how we can reconcile this change at the surface with the storm track intensity itself. So that's the too cold case, where it's really global mean cooling that's going to weaken the storm track via a decreased surface heat exchange gradient. Let's move on now to the too warm case, where we have two sort of timescales in mind: the near term with the melting of sea ice that decreases the albedo and increases evaporation in the Arctic, and then the longer term where the oceans warm up, and that has further implications for evaporation. So again, we're going to start with a qualitative hypothesis that for the Arctic sea ice loss part of the story, it should weaken the intensity because it increases the surface heat exchange in the polar region. So let's build upon this box model diagram to give you some intuition for that hypothesis. So here is once again the modern box model, and then we warm the Arctic. We melt the sea ice and thereby warm the Arctic, revealing a darker surface underneath that absorbs sunlight and allows for more evaporation. So we've increased the length of that blue arrow in the Arctic. And as a consequence of that, all else being equal, the blue arrows now have a smaller equator-to-pole gradient. And if everything else is equal, and we assume that the dominant rectification has to come through the storm track intensity, the black arrow, that must get weaker because the equator-to-pole gradient is weaker. And so that's what I just said in words here. That we would expect intuitively the intensity goes down. And as we've argued before, this is not something we really could have gotten out of in temperature-based frameworks alone. We can also make this quantitative, however, because while here we don't rely on Clausius Clapeyron, it's not a global mean type of a climate change, but what we can assume is that given the external changes of albedo, namely, we know roughly what the ice albedo is, and we know what the ocean albedo is. So the difference of that we can use to quantify the change of surface absorption of sunlight, and assume that when it increases would go directly into change in evaporation, an increase of evaporation. And so that's how we can quantify the prediction in this case. Now, in order to test it, once again, we have sort of three options. We can't go to the lab, so that's off the table. Now, observations is an interesting option here, and we have explored it. The challenges with modern Arctic sea ice loss is that it's extremely small in comparison to what we expect at the end of the century. And so while it's, of course, significant in the context of the modern time, from the perspective of, using that sea ice to infer a change and consider that the signal in the context of some background noise, the signal is much too small, okay? The noise is much too large. And so rather than focus on observations, here once again, we moved toward the self-consistent test with models, where we can amplify the signal by prescribing the Arctic sea ice loss at the end of the century, from 2085 to 2099, following a business as usual emissions scenario. And these are actually simulations from Mark England that he kindly provided to us. And so we're going to look at the Northern Hemisphere storm track intensity response to Arctic sea ice loss and the annual mean. And so here's again our bar chart. If we look at this end of century response to Arctic sea ice loss, it's 4.5% weakening. So, even that is a small signal, but within the context of these simulations, it's significant. And so the intensity change is a weakening as we intuited, and when we follow through this change in albedo and quantify it as a prediction through the change in evaporation, that's about just over 3%. So we are predicting a weakening that's not terribly far off of what we're getting. But to truly test, we want to compare it to the surface heat exchange contribution from the model itself, which is shown here, and that is close to 3%. And part of that is that the Bowen ratio, contributes, but not as much as it did in the snowball climate. And finally, the other two contributions, radiative cooling gradient doesn't really play a role here, but the stationary circulation does play a role. And so that's another important term. But really the dominant effect is the surface heat exchange contribution, and that, as we said, has some causal connection to the change in albedo. So let's move on then to the second case of this too warm climate, where we globally warm the planet and instigate changes in the subtropical oceans where evaporation is already largest. So again, the qualitative picture we build off of is the modern box model. And we now, rather than just change the Arctic region, we're going to globally warm this box model. And this has a pretty important consequence, especially, as I said, in this low latitude subtropical region, because we know evaporation will increase, and warmer air holds more moisture, but it really is a function of the temperature you start at. And so because we have a very warm region in the subtropics, we expect, as we'll see from the nonlinearity of this Clausius-Clapeyron relation, evaporation will increase much more in the low latitudes than it will in the high latitudes, because the starting point, the temperatures are much different. And so in the end, what happens is that the equator-to-pole gradient is strengthened, and that's really the basis of strengthening the increased surface heat exchange. And once again, all else being equal, we would have to, this hypothesis assumes that the storm track intensity would increase to help re-equilibrate the system. And so here's that change that I've just highlighted qualitatively in words, that the increased surface heat exchange gradient will increase because of the evaporation, and that will intensify the storm tracks. So we can make this quantitative, again, leveraging off of global mean changes in temperature, but this time not the cooling end, which was to the left. Instead, now we go to the right. So starting with the just right climate in green, we warm everything by 4 Kelvin as a nominal change here. And you can see that by doing that, we've steepened the slope, okay? And that's a function of the fact that this is a nonlinear exponential relationship. And so global warming creates a larger equator-to-pole gradient of the saturation specific humidity, which should, again, assuming the assumptions as I'll show, should increase the equator-to-pole gradient of evaporation, and also therefore the equator-to-pole gradient of surface heat exchange. And so that's how we make this quantitative. We take the surface heat exchange and assume that once again it follows evaporation, neglecting changes in the Bowen ratio. And then here we follow previous work by Schneider et al. And incorporate not just the change in saturation specific humidity, which is from the Clausius-Clapeyron relation, but also the change in relative humidity, which I will acknowledge we have less, complete theoretical understanding of. But following this combination of terms in Schneider et al., the expectation is that evaporation, and therefore also surface heat exchange in our assumptions, should increase at a rate of 2.5% per Kelvin times the global mean temperature. So again, not factoring in any temperature gradient change in this prediction. And so let's go ahead once again and test the prediction. We can't put the Earth in a jar. We don't have any observations of the future, so we rely on, once again, simulations of the climate system, now taken from the so-called coupled model intercomparison phase 5, which were models that were the basis of the Intergovernmental Panel on Climate Change 5th Assessment Report. And we take two time periods, a modern or historical time period with historical forcings from 1979 to 2005, and then, the response to the business as usual high mission scenario, or CP 8.5, late at the end of century 2073 to 2099. And I'm going to show you results for 21 of these models that provided daily data, which we need to calculate the contributions that I'm about to show you. And so in this case, we're going to shift to the southern hemisphere and look at the change there, because in the motivation slides, I showed you that, well, Paul O'Gorman has documented that the storm track will intensify, but that intensification doesn't follow the near surface temperature gradient. In fact, the ED growth rate was mostly a weakening. So let's target that particular disconnect to see if we can make progress. So here is our bar chart for the southern hemisphere annual mean storm track intensity response to late end of century business as usual emission scenario. So even at the end of the century, the change is 7%. So, this is also fairly small compared to what I started, which was the snowball, very dramatic decrease, 65%. So here it's a 7% increase at the end of the century. And the surface heat exchange prediction based on 2.5% per Kelvin times the global mean temperature change, which for this time period averaged over these models is 3.5 Kelvin. So that leads us to a 9% increase. So that's the basis of this roughly 9% increase. And when we go and, quantify this prediction, test it against the simulated surface heat exchange response, there we see even larger change, about 12%. And the discrepancy there, once again, is tied to changes in Bowen ratio, which do contribute an intensification this time. And then the other two terms, radiative cooling gradient between the equator and the pole, is the opposite sign, and the stationary circulation is, as always, pretty negligible in the southern hemisphere. So once again, surface heat exchange is the term that's in this decomposition, but also in the predictive sense, we think we have some causal understanding for its dominance. And so I just want to mention that the intensity has been obviously the focus of the talk, but briefly, we've looked at the change in the position of the storm track, which is expected to shift forward. And if we just focus on that for a minute, Zhihong Tan has showed that if you look at the poleward shift in degrees, so negative means toward the South Pole on the y-axis, it also is a strong function, or significantly correlated with surface heat exchange contrast between the equator and the pole, where each of these x's is a model from this CMIP5 ensemble. Okay, so let's summarize the response to too warm, which is that the Arctic sea ice loss has a weakening effect on storm track intensity because it decreases surface heat exchange, because there's more evaporation in the Arctic, and that global warming is really the opposite of global cooling. We strengthen the storm tracks via the increased surface heat exchange. And that largely follows because of the nonlinearity of Clausius-Clapeyron. And so just before I wrap up, I'm going to focus on just right, which might seem a little counterintuitive, because in the previous two cases, I've taken, the difference of too cold minus just right and, too warm minus just right. But just right is interesting in and of itself. And there are differences. Particularly, we're going to look at differences between the hemispheres. So there is a significantly different seasonality. Northern hemisphere has more seasonality than the southern hemisphere. But I'm just going to talk briefly now about the differences in the annual mean storm track intensity. So here is the reanalysis quantification of the differences in the hemispheric storm track intensity. So southern hemisphere minus northern hemisphere in this mid-latitude band as a percent. So it's about 33%. The southern hemisphere is stronger by 33%, which is obviously larger than climate change, too warm climate change. And so when we go ahead and decompose this, and these terms should of course be calculated with other reanalyses, but we find for the surface heat exchange in the era interim, this is provided on the order of just about 15%. And radiative cooling gradients between the hemispheres is not significant actually, and that's also consistent with top of atmosphere radiation. And so where the other half comes from is the stationary circulation In the northern hemisphere, there's a very significant stationary circulation due to land-ocean contrasts and topography, and that leads to a significant poleward heat transport. And that doesn't happen in the southern hemisphere, and so that contributes in terms of this decomposition to strengthening the southern hemisphere storm track relative to the northern hemisphere storm track. And so once again, the surface heat exchange plays a role here, but obviously stationary circulation is on equal measure. Well, I'm just going to wrap up then, summarizing what we were trying to do today. So we were, interested in answering this question: what controls storm track intensity? And realizing when, looking across this broad range of Goldilocks climates, that the equator to pole near surface temperature gradient really couldn't give us the right answer all of the time. And so we decided to move away from just to focus on that and think more about changes in the boundary conditions, and that led us to this focus on surface albedo and surface heat exchange, and then building up a framework that could include the connection between changes in those boundary conditions and the storm track intensity. And then, of course, we've applied it to these three climates. And so then, just in summary, in each case, surface heat exchange played a really crucial role. When we talked about the too cold Goldilocks climate, we really, here we're instigating global mean cooling and its effect on weakening storm tracks because of a decrease of surface heat exchange that was fundamentally connected to evaporation and the dependence of the saturation specific humidity on global temperatures. And then if we shift back over to too warm, we saw this interplay between short time scales where Arctic sea ice loss would weaken the storm tracks due to a decreased surface heat exchange gradient, whereas global warming, being the opposite of global cooling, it's going to strengthen storm tracks via increased surface heat exchange as a consequence of the nonlinearity of Clausius Clapeyron, but moving toward warmer temperatures. And then finally, in the just right case, we've examined these hemispheric contrasts and seasonality and annual mean, and it's clear there that also surface heat exchange is important for hemispheric contrasts. So with that, I'm happy to end here and take any questions that you might have. Thank you very much.
Thank you, Dr. Shaw. If anyone, Mike Evans has raised his hand. Mike, you are unmuted.
Oh, sorry. Thank you so much for this talk and for taking the time to visit with us. I had two somewhat related questions. The first was that you framed evaporation as a function of surface heating, but I'm used to thinking of evaporation in also in terms of wind stress induced effects. So I wonder if you've thought about that term. And the second thing which is kind of related, is we don't have very good data perhaps for the Snowball Earth, but we do perhaps for the last glacial maximum. So I wonder if you've thought about what you would predict for the last glacial maximum when we think we have dustier conditions, which probably means windier. Thanks.
Great. So yeah, definitely. Thanks for those two questions. Let me start with the first one. So yes, indeed, in the context of evaporation, one should be considering not just, there's potential changes not just from relative humidity, or also changes, as I've focused on, the saturation specific humidity, but there is a dependence and potential importance for changes in surface wind, near surface wind. We find those changes to be small. So this sort of builds on that Schneider et al. Paper, which is a review paper that I referred to. It came out in 2010. And that seems to be the general case. Him and his colleagues, they looked at a wide range of climates in an idealized simulation. But when we go and quantify that particular term, the contribution of near surface wind changes to evaporation for these particular, Goldilocks climates, as I've described them, it's a small contribution. But yeah, something that we can definitely check, and we should always quantify. And then yes, the other climate that one could add here would be the last glacial maximum, which has the virtue of having, at least being closer in proximity to the modern, and therefore having more paleo proxy data available. And so that's definitely on our radar. We have thought about a lot about, because there is a temperature gradient increase in the North Atlantic that has been documented, but the storm track intensity as simulated by in the Paleo model intercomparison project. Climate models also simulate a weaker storm track there. So this is another big puzzle, and there have been various ways of trying to reconcile it. And I think there is a potential role here for the same type of global mean cooling arguments, but obviously applying them in a basin will require some further thought, North Atlantic basin in particular, further thought about, the role of lateral boundaries. That's what happens if you take the framework and the ideas I've just put forward and you carve out, rather than averaging over all the longitudes, just a basin. One needs to account for those lateral boundaries. So I think the hypothesis would be the same as global cooling, but what remains is to go ahead and test it and quantify it. And as I said, that's definitely something on our radar. So thank you for the questions.
That's what I thought you were going to say, but I wonder if my third question, I'll stop, is
Sure.
I wonder if the ice sheets and particular positions make the role of the stationary waves more important because they're so tall and so continentally trapped.
So that would, yes, and that definitely has been put forward several groups have put forward that as a potential reason for the weaker storm track, even though temperature gradient has increased. And in fact, we could quantify it as part of this framework too. So I was more trying to highlight the connections to this talk, but you're absolutely correct. Where it would appear in this quantitative decomposition, as I've put forward here, is in that stationary circulation term. So by testing the hypothesis, if I were trying to rely once again on the evaporation and global mean cooling, I would be comparing that particular term to the previous, the previous mechanisms associated with the stationary waves, which would be the stationary circulation term. So I think this framework is a good way to really compare and contrast, mechanisms, not just build a framework for one mechanism, but also have ways of saying, okay, that's where that mechanism would appear, and this is where the other one would. Let's quantify them now. So you're right, there could be still a significant role for the stationary circulation, and we could compare and contrast that with the evaporation changes I've discussed for global cooling.
Thank you.
Thank you, Mike. We also have a question from Ron Miller, so I'm unmuting him now. Okay, you should be unmuted, Ron. Yeah.
Yeah, so this is a very elegant theory, Tiffany. I mean, I really like the idea of Clausius Clapeyron scaling and how the global mean temperature is very important, not just the temperature gradient, which seems kind of counterintuitive at first, but you explained it very clearly. I'm wondering whether the warm and the cold climates, they seem like they have very different amplitudes compared to the present day. I mean, the snowball climate is much different than the present day climate compared to the perturbation, in the warm climate. I'm wondering if there are any nonlinearities that were, more apparent in the snowball climate. I mean, do you think there are any? I guess I'm just going to ask if there's any kind of amplitude specific behavior that you noticed.
Yeah, not in particular. I think what would be interesting, though, to get at your question, and there's a little bit of a discussion of that again in the Schneider review paper with respect to the hydrological cycle across a continuum of climates. Here, I'm just, of course, taking specific samples. The most things, though, vary pretty smoothly. The nonlinearity, there is, of course, some potential for nonlinearity with respect to OLR. That's another possibility through the Stefan Boltzmann, and I guess also surface long wave. But the changes in radiation, while they can happen both at the surface and the top of atmosphere, they don't really seem to, they seem to offset each other to some degree. And so in the net, radiative cooling or TOA fluxes in total, people have talked about this invariance with climate, or rather Peter Stone, that it's more or less rather flat. And here, yes, we do see a big decrease in the total flux, but it doesn't seem to be coming from the radiation part of it alone. So yes, looking at more nonlinearities in more detail, I think would be interesting, and I think it would help to have a continuum of climates rather than just sort of three three particular instances.
Thank you.
Thank you. Does anyone else have any questions? You can raise your hand or just chat me and ask to be unmuted.
Ron, were you thinking about clouds?
Well, my understanding is, I mean, I'm sorry.
Oh no, I'm sorry. I didn't realize I didn't realize you guys were still there. No, carry on.
Sorry, Mike, was that a question for me? I guess I was thinking about the snowball climate, and Pierre Humbert found that clouds were really there were very few clouds just because it was so cold that there was not a lot of water vapor in the atmosphere.
But
Yeah,
that might not be, oh, sorry.
Yeah, so clouds are another thing we can certainly quantify in this framework if we wanted to separate radiation into, in a model, very straightforwardly separable into clear sky and all sky. But the strange thing about clouds obviously is they're not external either. The atmosphere is moving them around, and Iko Voigt has done a lot of nice work on that problem. I think what amazes me, and again, this is not that I understand it causally, is that even in terms of the cloud, in terms of planetary albedo, it's quite symmetric between the hemispheres. And so in this hemispheric contrast thing that I ended off with, that's not necessarily, understanding why that is the case is not trivial, but it is very hemispherically symmetric, even in the modern climate. The total radiation, the cloud part of it, and I think that is something that needs to be further understood. But as a consequence of that, it doesn't really contribute much, whether it's this hemispheric asymmetry, or if you look at the future where people have argued for changes in shortwave or longwave cloud radiative effects. Again, if you take the total atmosphere radiation rather than separate longwave and cloudwave, long wave and shortwave, yeah, we don't see a big net effect of clouds. But certainly I acknowledge you can decompose these energy fluxes in different ways and leverage them differently.
Okay. Seems like nobody else has any more questions, but you can always raise your hand really quick and I will change that statement. But anyway, thank you everybody for coming, and thank you, Dr. Shaw, for giving us this great talk. Please, everyone, have a good evening and come back next week for the last seminar of the semester. Thank you.
Thank you.
Thank you, Professor Shaw. We will send you the video recording once we get it. Thank you so much.
Okay, take care. Thank you.
Take care. Stay safe, everybody.